Hi, I'm Norwich from UCIT. Today I'll be introducing my work on MegaRPC, hardware-assisted efficient memory management for processing mega-sized RPCs. In this work, we focus on RPC framework over TCP on the internet. TCP over the internet can experience connection drop and often packet loss in the middle of the stream. Systems such as embedded system and machine learning system are often loosely connected, so RPC is used to send data of various sizes, such as machine learning model over the network. There's also an issue of packet fragmentation at different layers where different maximum transferable units are enforced. So it is hard for the receiver to adapt to these changes during the transmission phase. Packet arrival event has to be processed by the CPU. It got pulled out of the receiving queue from the network interface card and placed into the reserved memory region during the DMA process. This process can be optimized using kernel bypass solution. However, it's up to the application to deal with the memory footprint during the packet receiving process. Problems such as cache stall and TLB misses could arise due to context switching. From this chart, previous work showed that the Linux kernel spent more than 2/3 of its time on socket I/O and TCP connection maintenance for one packet request. Such high I/O overheads needs to be improved. So, why hardware? With all these advancements in kernel fastpath and bypass solution, one key missing link is to understand the changes introduced at the software level and look at how the hardware can be optimized for user-space application. We begin to understand the limits of kernel bypass solution. Previous work has shown that the spinning cores waiting for packet arrival doesn't scale well under unbalanced traffic due to constraint in cache and memory capacity. User space application receive the packet out of order, so it also wastes CPU cycles for packet reassembly as well. Let's look at our MegaRPC solution. We introduce a memory indirection table that can be easily incorporated into the memory I/O controller hardware and doesn't take much space and incurs small processing penalty. The table contains information to steer packets to the memory region set up by the operating system for the RPC request. First, we have the region pointer where the address of the memory region is allocated for the RPC request. And second, the information on where this packet should be placed in that memory region. The goal of the memory indirection table is to relieve the memory bookkeeping operation away from the CPU, and filling and updating a record in the table is done by the memory I/O controller, so no CPU interruption is required. Second contribution is perforated paging mechanism. Since TCP allows out-of-order delivery, however, a packet is placed in memory upon order that they arrived. So we introduce bitmap array for missing packets, a sequence of bits representing fragmented area which tells the information of where the missing packet might be placed at what location. This information can be used as a hint to the CPU to calculate the offset between the starting of the huge page region and directly place the packet to the correct location. So we implement MegaRPC in Gen 5 because we are introducing a new hardware components in the memory I/O controller. We expect our work to provide the following benefits. Our main goal is to reduce memory operations spent on the CPU so that the CPU can do other useful work. Since packets are served as a whole, the application doesn't need to do packet reassembly. One could also build a monitoring framework to monitor the bitmap array and estimate the time of all the packets' arrival for such requests. Finally, as our future work, this metadata table will help us with determining if the packet can be pre-processed while waiting for the missing packets to arrive. Thank you very much, everyone. I'm looking forward to discuss our work in the workshop.